Paalala, ang bidyong inyong mapapanood ay hango sa mga naintindihan at na-carrybles ng aking brain cells. Ang anumang maling impormasyong mababanggit ng inyong yours truly ay hindi sinasadya at nagkataon lamang. So, handa na ba kayo? Sa loob ng 10 segundo, pakitipa ang mga letrang RG at isend sa ating chat box. Marahil nagtataka kayo, bakit RG? Ang RG stands for Riemannian geometry na ginawa ng inyong tito na si Bernard Riemann na isang German mathematician. Bernard Riemann was another mathematical giant hailing from northern Germany. Poor, shy, sickly, and devotedly religious, the young Riemann constantly amazed his teachers and exhibited exceptional mathematical skills, such as fantastic mental calculation abilities from an early age, but suffered from fear of speaking in public. Fortunately, to have a school teacher who recognized his rare mathematical ability, the teacher lent him advanced books to read, including Legend's number theory, and after a week, Riemann claimed to know it by heart. He also continued to study the Bible intensively, and at one point even tried to prove mathematically the correctness of Book of Genesis. Although he started studying philology and theology in order to become a priest and help his family's finances, Riemann's father eventually managed to gather enough money to send him to study mathematics at the renowned University of Göttingen in 1846, where he first met and attended the lectures of Carl Friedrich Gauss. Indeed, he was one of the very few who benefited from the support and patronage of Gauss, and he gradually worked his way up the university's hierarchy to become a professor and eventually head of the mathematics department at Göttingen. Among his many contributions, he is notable for the Riemannian integral, as well as being the first person to rigorously define the integral, the analytic continuation of Euler's zeta function, the Riemann hypothesis, which is probably the unsolved conjecture in number theory, Riemann surfaces, which made a strong link between topology and complex function theory. Ayan, may meme. And of course, the Riemannian geometry, which was the fundamental in Einstein's general theory of relativity. So, what is Riemannian geometry? It is the branch of differential geometry that studies curved surfaces. So, for the bonus question, for 10 seconds, give an example of objects with curved surfaces. So these are my examples of objects with curved surfaces. A soccer ball and a saddle. One of them is spherical in shape and the other is hyperbolic, and both of them are classified as non-Euclidean geometry. So speaking of Riemannian geometry, it is also called in some accounts that I've read as elliptical geometry, and others call it spherical geometry. While the hyperbolic geometry was developed by Bolyai and Nikolai Lobachevsky. And to further understand the characteristics of Riemannian geometry and how Riemann developed it, let's watch a short presentation.
Riemann saw that there were other possibilities for non-Euclidean geometry. The simplest was the case for postulate 5 of Euclid, the case in which lines whose interior angles add up to exactly 180 degrees don't stay equidistant but actually gets closer to one another. How?
Think about the lines of a longitude
on a globe. You can lay a line across them that should make them parallel by our Euclidean postulate, and yet they all intersect. Any line of longitude you choose will cross all other lines of longitude at the poles. In fact, the very idea of lines starts to break down. If your flat plane is actually a globe, you simply can't draw a straight line. As soon as you start to extend that line at all, it has to be a curve. So like Bolyai and Lobachevsky's hyperbolic geometry does strange and unnatural seeming things to our shapes. When you add up the angles in a triangle, how many do you get? Well, on a normal Euclidean plane, the sum is 180 degrees, but on a spherical surfaces, our triangle's angles add up to more than 180 degrees. Most people at that time, even today, seems uncomfortable, wrong, or just hard to grasp. Kaya siguro may naniniwala pa rin na ang Earth ay flat. So, ang ginawa ni Riemann, nag-lecture siya nung 26 years old siya para sabihin yung idea niya na magpapabago ng lahat. Instead of just proposing hyperbolic or the geometry of spherical space, Riemann proposed that there were infinitely many possible non-Euclidean geometries. And there, he began to lay out what would become a system to unite them all. Riemann suggested that there were mathematical ways of looking at them all, no matter how weird or how complicated. And this is incredibly important because by having a unified theory of non-Euclidean space, regardless of dimensions or shape, it means that non-Euclidean geometry might no longer be just a mathematical curiosity.
So to summarize the Riemannian geometry in the video, the geometry is in sphere, the sum of the angles of the triangle is more than 180 degrees, and if you notice, Riemannian geometry have curvature. Another definition of Riemannian geometry, it studies manifolds with metric tensors. Manifolds sa madaling salita is any object that is nearly flat on a small scales that we can see. So in the image, for example, our object is sphere, and if you zoom in, the small scale that is nearly flat is the manifold. So nabanggit kanina sa video na Riemann suggested that there were mathematical ways of looking non-Euclidean geometry. So ang ginawa niya, he developed the mathematics for this generalized space with any number of dimensions. Basically, it is a three-step process. First, we define the metric for the space that allows us to measure distances. Second, we use the distance metric to find the geodesics for the space. And third, we use the geodesics to define what we mean by curve.
So assuming that we have a curved surface, and if we zoom in, we will have a smooth manifold, and in that flat space, distance between any 2 points is defined by the Pythagorean theorem. But if we have different scales, I mean its stretch or its axis is not perpendicular to each other, that knowledge is not applicable. So Riemann generalized it by adding coefficients to take into consideration the different scales for lines in different directions and the fact that the lines no longer cross to form right angles. These coefficients are put in a table and we call this the metric tensor or the G, and its components are numbered by two indices. And finally, we extend the number of dimensions and generalize the coefficients to be functions of locations to take into account curved and changing coordinate systems. This generalized metric tensor is the foundation for non-Euclidean geometry, its geodesics, and its curvature at any point. The shortest distance between any 2 points is straight line if we're dealing with Euclidean space. But in the context of non-Euclidean, the shortest line between any 2 points is called geodesics. So to visualize, yung dalawang points natin is yung Los Angeles at yung Paris. Ngayon, yung airplane is moving the shortest straight line called geodesic. So baka kasi nagtataka kayo bakit curve yung nakikita nyo pero sinabi kong straight line. Remember that we use the Earth's surface that has a latitude and longitude coordinate system na kapag titignan malapit sa konsepto ng geometry. And gusto lang natin na lumipad yung airplane na yon ng straight line. Kapag hindi natin pinatigil yung lipad ng airplane, yung mabubuong straight line is magiging great circle. Ngayon, kapag nilatag natin yung sphere, ang mabubuong image is curve. Pero ang totoo, straight line lang talaga siya. So, yung catch dun is yung coordinates ng grid natin is curve and yung axis is hindi nagko-correspond dun sa coordinates na straight line on a sphere. With the metric tensor, we can measure distances between any 2 points by adding up all the small distances along the way. Taking the formula and finding its minimum is an exercise in calculus and gives us the shortest distances. These are the geodesic lines. Now that we have a way to measure distance and find geodesics, we can determine a space curvature. Riemann used a concept called parallel vector transport.
And for our bonus question, complete the statement below. This is for 15 seconds.
So, to illustrate, may plane ka with square grid and yung sphere with latitude and longitude coordinates. Ngayon, lalagyan mo sila parehas ng identical vectors and itatransport mo yung vectors ng up or down, left or right. Kung mapapansin nyo, yung square is hindi nagbago yung image ng vectors kahit na anong direction yung mauna. Unlike sa sphere na nagbago yung image. That effect is called curvature. Dahil may concept na tayo ng curvature, we can express it mathematically. Riemann developed the tensor that precisely measures how much the components of a vector change when it is parallel transported along a small closed curve. This is called the Riemann curvature tensor.
So to wrap up the things that I've discussed, the metric tensor is a function which tells how to compute the distance between any 2 points in a given space. A geodesic is a local length minimizing curve, and the Riemann curvature tensor, which is a tool used to describe the curvature of n-dimensional spaces, such as Riemannian manifolds. And these made up Riemannian geometry itself. Hope that you gained something from me. Thanks for listening.